Hi, everyone. My name is Shammah. I work at the Unitary Fund, and today I'm going to give you some updates from Mitiq, the quantum error mitigation toolkit that we are developing with a broad network of contributors. So I will share later on also link to slides and to the tutorial I will show. So let me start though with really 2 minutes of introduction to what Mitiq is, in case you're not familiar. Mitiq really starts from this premise that if we want to simplify as much as possible what happens when one runs a quantum program on a backend, this is a workflow. We obtain an expectation value upon executing a quantum program, which in the simplest form could be through the means of a quantum circuit on hardware or simulator. And several error mitigation techniques that have been developed by research teams, including prominently at IBM, also Unitary Fund and other places, basically make this workflow a bit different, but still quite simple. And this is the absence of an active feedback in general is the main difference with respect to error correction. So QEM here represent error mitigation. And one generates many programs, so is able then to do sort of like a sampling of different results, noisy results, and then with a fully classical technique is able to obtain an error mitigated result. And with Mitiq, we have several techniques that are supported. Here you see some of the modules with respect to, again, divided between the intermediate circuits compilation and the inference part. I will explain a bit the acronyms in a second. Let me just mention that given the state of affairs of the current ecosystem, we strive to really support as many front ends as possible for folks who want to really use their workflow and insert Mitiq in their use case. And the backends are basically any backend, because the way we wrap the use of Mitiq through executors really does not require to have specifications about the backend. So that is a part that is not really touched by Mitiq. And then the inference part is that it's like we just need to collect B strings or error mitigation values. And here in this plot that if you squint, you can see like a yellow graph that goes down, while there is the one that is close to the ideal value as the number of qubits increases, and this is and also the depth. And so this is like an example of the use of error mitigation, and we've been benchmarking this in many papers, including the latest one uploaded on the archive in last October. So now let me come to the last 2 slides before jumping to the notebook. So Mitiq has a very comprehensive documentation that you can find at mitiq.readthedocs.io. It is distributed on PyPy, so you can do pip install Mitiq to start playing with it. The project started in 2020. It has now 75,000 downloads, over 50 contributors, and only about 10 come from a Unitary Fund team. So we're very happy about this ratio. And here is really like an overview of the major techniques. Of course, in this tutorial, I cannot get into the details, but basically imagine figure Mitiq as a Swiss Army knife that allows you to pick one or many or combine many of these error mitigation techniques and apply them to the workload of interest. Zero noise extrapolation, probabilistic error cancellation, Clifford data regression, dynamical decoupling at the gate level, which we call digital dynamical decoupling, and without error mitigation are the major techniques. And here you see the acronyms that specify the modules referring to these techniques in Mitiq. And there's also a white paper recently published in Quantum, which provides more theoretical background and examples. So what I'm going to show today is updates from two recent versions released on the README in the Qiskit Demo Days. We were mentioning 0.23, which was released on beginning of February. But since a couple of days ago, Misty Wall from the Unitary Fund technical staff, as milestone manager, released the 0.25 release. As you can see, we have a quite steady pace of release every month. So what are the updates from these two releases? Actually, they're quite coherent. So we refactored and added improvements to a Mitiq calibration module, adding also information to the user guide. So this is a still work in progress module, but I want to show you in the tutorial how this can help using quantum error mitigation and choosing the best quantum error mitigation technique. So we're really excited about this new module. And other updates in these two releases refer to the refactoring of the readout error mitigation module and extended documentation. I really want to thank Amir Ebrahimi from Unitary Fund Ambassador. So these are volunteers that really pushed with these request for comments document, and also deploying the technique, and now giving like very great explanation with documentation. And then there is 3 tutorials, 2 on dynamical decoupling added by Misty Wall, 1 working with Circ, 1 with Qiskit, and the one with Qiskit has been already used internally to prove that this can be used out of the box to improve results on real hardware. And 1 tutorial was added by Purva Thakre, another volunteer and Unitary Fund ambassador, and it is an update of a lab exercise that was used in a summer school in Florence last summer during an interactive session chaired by Andrea Mari. I really want to thank Nate Steeman from the Unitary Fund team for really driving forward the calibration module updates. So now, just before starting with the tutorial, I just want to show you in a second this page that you can find on the Mitiq readthedocs.io website with a series of examples. And this is a great place to start tinkering with Mitiq. So I just wanted to hint at this, and the tutorial I'm showing today as a preview will be added here. It's also a good time for questions if there's any, but I don't know if that's in the format of these updates, which are pretty brief.
This is actually really great. Yes, it's also good to have a preview on what you're going to have published soon.
Oh, okay, great. So yes, so here now you should be seeing the Jupyter Notebook, and also let me share here a link in the chat where you can find this notebook. A link to a GitHub repository with a notebook, and then you can also find it on Google Colab or My Binder in case you want to play with it, and it should be already working. Okay, so let's import the functions, and the scope of this notebook is really to give an overview of what we mean by quantum error mitigation calibration. So let's import some standard functions. There's no time now to really say why we need to import this and that function, or actually, sorry. Yeah, let me check. Yes, never do live coding. It's the first lesson of live coding. So let's import a function, and let's define a quantum circuit of interest. So let's suppose we want to deal with 2 qubits, with a depth of a circuit is 20, And let's fix the number of shots to 1,000. It's not too much, but I wanted something quick to run here. And we want to define a randomized benchmarking quantum circuit. So we have a function in Mitiq called generate RB circuits inside the Mitiq.benchmarks module that can be used exactly to define this sort of like standard workloads. We have other examples for quantum volume, GHZ states, and so on and so forth. And here you can see the quantum circuit as generated with Qiskit and with measurements appended at the end. So now I define an executor, which is like a standard function that very simple that can be defined by the user, and it's what is consumed by Mitiq. It has as input a quantum circuit, and then returns an expectation value, a noise expectation value, because we want to correct noise. And in this case, I'm using a simulator from the IBM Quantum Backends, which is a fake Jakarta. And for number of qubits and shots, I'm using the general details that I define as the global variables in the top. So now I apply error mitigation with Mitiq, and this can be done with the execute with ZNE function, which takes the circuit and the execute circuit function just defined on the top. So this is the standard way of using Mitiq. And here, the seed has been graceful with us because the ideal value, well, the mitigated result is closer to the ideal value than the mitigated result. Again, this is not the optimal amounts of shots. But now we come to the real point, which is it's quite tricky to know exactly with what parameters you should apply execute ZNE. Now we could say to some extent that we were lucky because the parameters that are set by default were able to effectively mitigate the randomized benchmarking result, which we know it's 1. But what if this is not the case? So that's why the calibration module comes into effect. And let me just define here a function that is consumed by the calibrator. I will not go into the details, but let me just mention that this is really fresh. And so we haven't really fully built a support for Qiskit quantum circuits for how the calibrator works in the backend, but this is on our roadmap. And this is all we need to say with respect to this function. And this function will be used by Mitiq.calibration, which has a calibrator class and some settings. And then the execute with mitigation will sort of like replace the execute with ZNE, which stands for execute with zero noise extrapolation, that I've shown in the past. So in order to run the calibrator, we need to define some settings in this settings class that we want the calibrators be the parameters among which we want to look for. There's also default setting, which is called ZNE settings, but it would take a bit too much time and it was not really tailor-made for the example that I'm showing here that is very simple. And so I defined a new setting object, which, as you can see, has two main parts, benchmarks and strategies. So the benchmarks are the sort of circuits that are used as a benchmark by calibrator. In this case, I'm using randomized benchmarking circuits, also because what we want to run eventually is a randomized benchmarking circuit. And the strategies, here is where it comes all the fine-tuning and knobs that are typical of Mitiq. They can be scale noise factors and methods, different ZNE so-called factories, so strategies to apply zero noise extrapolation for extrapolation. And here you can see some details. So ZNE applied with global folding on a Richardson factory with these scale factor parameters. And so on and so forth, we change some other details. And now we run the calibrator, and with a log equal true option, we will start to see the results coming from running this calibration. So here you will see that there is 8 noisy executions as defined by the settings above. And you will see a green tick or a red cross in case the mitigation actually is improving or not with respect to the idea result. This time we were sort of like lucky because we're all green ticks. And then based on this sort of like test with different possible outcomes, we're gonna use execute with mitigation, calling this calibrator, which will apply the best technique that has been found out of this. So the one that is providing the most improvement with respect to the many that were tested here. And so here we apply it, and we compare it to the mitigated and unmitigated case. And it will just take a second to run. And okay, this is wonderful because this was not, again, given the small sample, it was not provided that it would work as expected, but it did. So the ideal value in this case is 1. The mitigated value with noise is 0.96. If we apply error mitigation out of the box with execute ZME, we get an improvement because this value is closer to 1 than this other one. But if we use as knobs the one that have been found as optimal strategy by the calibrator, we get an even better result. And so in summary, this is an example of using quantum error mitigation with calibration using this automated technique present in Mitiq.
Thank you. Any comments or questions?